Good morning again, everyone. Thanks for coming. I'm Stinger Gwala from NASA Earth Science Data Systems, and welcome to Enabling Scalable Global Open Science with the Multi-Mission Algorithm and Analysis Platform and other spatial data infrastructures, as we call it, the MAP Symposium. The Multi-Mission Algorithm and Analysis Program MAP I'm the coordinator for it at NASA. It's NASA's flagship product for open science and open source science. It's also one of our flagship products showing it's a very tight collaboration with the European Space Agency. We have built this together. And I tell you, it's the most collaborative project I've ever worked on. It's amazing. We have a stellar group of speakers today. They're all really at the top of their game, and I am so honored to have them on the team. You know, it's really, I mean, wait till you see. They're awesome. And we've got Dr. Clement Albanese coming in from the European Space Agency as well to talk about the European side of this. So, and also I did want to point out that, you know, I'm the co-chair on this symposium, but Doug Newman here has done all the work and deserves all the credit. So we're very grateful. Our first speaker is Amy Barsiekis. And Amy's one of our lead developers in the data area. Take it away, Amy.
Thank you. So I'm going to be presenting a brief survey, brief being the key word here. Doug's going to poke me when I run over 13 minutes. So there's a lot to talk about. I was at ESA's Living Planet Symposium in May with a bunch of other folks that were here. And I was inspired to basically start this survey given everything that I heard there. So for those of you who don't know me, my name's Amy. I usually work in Seattle at a company called remotely for a company called Development Seed, but most of my projects are with this group, NASA Impact. Okay, so the idea. So a recent influx of new Earth observation exploitation platforms caused a case of the apps, yet another platform syndrome. However, this new generation of EO platforms share common paradigms of interoperable standards, cloud optimizations, and open source tools. Sharing these paradigms means we can use and contribute to an ecosystem of EO exploitation tools, and we can customize new platforms using those existing tools, minimizing time spent on new developments. And this even means a future of a network of resources is in sight. So I'm going to simplify the problem by talking about how we can follow this simple equation to think about platforms. When you put data with software projects or programs, you get these platforms. We're going to go into detail about how to break down an EO exploitation platform, what are the components that make those things up, talk about some example platforms, and how do we get a simple roadmap for how do we get to a network of resources. So I distinguish projects, software, specs, working groups, standards, and actual platforms and their services which use these technologies for real use cases. So these platforms together and their projects can form this network of resources. So examples of projects, so these are the software things. These are not things that people actually do science on, but they're open source software like OpenEO, they're communities of developers like Pangeo, they're data infrastructures like Metadata has created for different science applications, and even the multi-mission algorithm analysis platform is a project. It's creating new software. So I was really excited when I heard about OpenEO processes. So basically this idea that if you have a standard for your data, like data cubes, you can create an existing library of simple data processes, and then you can put these together to form an algorithm. And then once you have those process graphs, you can use OpenEO backends. So even Google Earth Engine has an OpenEO compliant backend. So you can put together simple functions like absolute mean are examples here to create a more complex function. They call these user-defined functions or UDFs. So buyer beware, OpenEO is not equal to OpenEO platform. So I really liked this comment where basically somebody was trying to use their Google Earth Engine credentials to run Google Earth Engine credentials to run examples in OpenEO from the documentation. However, the OpenEO platform developer wanted to clarify with this person that OpenEO platform is not the same as OpenEO as the OpenEO open source API. GEE is a compliant OpenEO backend, but it's not fully implemented. You basically had to request like test credentials to use it. One really cool thing that OpenEO provides is this hub.openeo.org, which provides different example backends. So you can actually search for different functionality and different collection, and you get a result of what backends might possibly actually support your use case. However, a lot of these are not production ready. But the really great thing is OpenEO is a bunch of open source software. So if you wanted to implement your own backend, you could re-implement any of the OpenEO platform software libraries on top of it. So probably a lot of you in the room are familiar with Pangeo. I'm not going to go into too much depth about Pangeo, but just to make the point that it's really it's primarily a open source community focused on a certain set of software packages that I've enumerated here: Jupyter Hub, Czar, Xarray, Dask, and Pangeo Forge. And so now a lot of institutions and companies have sprung up to basically replicate these quote unquote Pangeo-like stacks. Something new I heard about at ESA's Living Planet Symposium is Dataterra. So Dataterra is really focused on the data hub aspect of an EO exploitation platform. So it's basically created these infrastructures for a specific environment domain. And so these data hubs are supporting different science domains that I'll talk about in a second. But I found the history pretty interesting. So basically they came together 2012 to 2014, a bunch of academic institutions and federal institutions within the French government did some working groups, and this led to the inclusion of formal funding for these infrastructures. They now have 4 data hubs focused on different science domains, and now they're wanting to make those things more interoperable through the Gaia data project. So these are the data hubs. They basically compose different science domains: atmosphere, land surfaces, solid earth, and ocean. And then these data hubs and the infrastructure overall is used to contribute to a number of other European projects. So what makes an Earth observation exploitation platform? Fortunately, somebody has come up with a set of use cases and common architecture for thinking about an EO exploitation platform. They came up with a use case analysis document, a master system design document, and an interface control document. They really bring home the fundamental point of an EO exploitation platform is to bring the user to the data. So you want to co-host your co-located computing and storage. However, they also propose that working with a set of open interfaces and building blocks, we can work towards a network of EO resources. So the common architecture will be defined using these open interfaces that link different resources so that a user can efficiently access and consume the disparate services of the network. So the common architecture starts with its use cases. So we have the breakdown of consumers and experts. I also think about this like data consumers and data producers. Then we have the host infrastructure. So this is all the compute and the data, the actual supposedly a cloud service that you're hosting this on. On top of that, you have your catalog and data services. So these are all the ways that users can explore the data. Separate from this would be the processing framework. So that's what you use to create new analyses. And then you expose all of these functionalities through an HTTP API, as well as client interfaces. And then you have web portals. Sitting across all of these services is your identity and access management. And then all of these components map to ESA's 3 ecosystem tiers of resource, platform, and exploitation. So some example platforms: MAP, OpenEO Platform, and Pangeo Cloud. So there's too many platform existences of these types of platforms to really go through. You can just continue to discover more and more. So I grouped them by projects, so you can sort of start to map different platforms into software projects that they might share use of. So here we have Dataterra again, OpenEO, Pangeo, MAP, and another one called Cloudpharaoh. So Cloudflare is a cloud computing company that sets up cloud computing infrastructures for not just Earth observation, but it runs two of ESA's DS, the Data Infrastructure and Access Services for things like Sentinel. So here we have Creo DS browser and Wekio, and then another EO exploitation platform that was set up for the German government, Code DE. So I have the most experience with MAP, so I'm going to talk about that in a little bit of depth, but the later speakers are going to go into more depth. So it is obviously a collaboration between ESA and NASA, and it's a science-focused virtual environment. And I just have this, am I able to play? Yeah. This one little video that I really like because it shows how we can integrate existing tools like NASA's Earth Data Search, where the user acts as a data explorer and discovers some data of interest by drawing a bounding box, and then they can take those search results into their notebook environment, and they can paste those search results, basically demonstrating how you go from a exploration into analysis. So what makes MAP different? So it's focused right now on above ground biomass estimation, but it's being used in new domains. We collaborate with ESA. We have these three different data platform and science teams that collaborate. So these cross-functional teams that collaborate. We use Eclipse Che, we use HiSDS, and we also are integrated with NASA's data system software, Common Metadata Repository, and Earth Data Search and Cumulus. So really wanted to make the point here that it's a huge group effort. We have these cross-functional teams from science, processing, and data systems, and none of these science results would be possible without having all of these people involved. So how do we get to a network of resources? So you might recall this diagram from before. So a network of resources really, to me, an example of what that would look like is a user of Platform A web portal discovers data on Platform B, sends application package to Platform C. So there's no one platform to rule them all. We don't propose one platform or even one stack. Again, the glue is this open source and standards that we can use to piece together different components from different platforms. So I really like MyBinder as a good model to follow for reproducibility. Any repo with a requirements.txt or a Conda environment can be used to launch via MyBinder, but there's no data processing backend to MyBinder. Can we expand the MyBinder model so any repo compliant with OGC application packages can be sent to a compliant processing framework? So here we can really focus on the work to go, being these application deployment execution services and data publication. And I believe Hook is going to go into these the implementation of what this looks like in much more detail. But on the left-hand side, you see the principal components for any application package could be common workflow language, paper mill, and stack. But the importance really here is using shared standards. We really hope that Platform B data and Platform C compute are using the same host infrastructure. Otherwise, we're going to spend a lot of time and a lot of money. So in summary, develop less, learn more. New platforms should bridge existing tools with science needs. So stay involved in the community, show up at things like this, learn about what other people are doing. Work on and use common standards for data processing, data has gravity, and then develop tools for data and algorithm publication, make it possible for users to share data, products and analysis, publishing user-defined functions. And that's it. Are we doing questions?
You got 2 minutes.
Cool.
Any questions for Amy?
Can you pronounce your last name?
Yeah, it's Barchauskas.
Barchauskas.
Yeah, like
I
chowder.
swallowed that.
No.
Test. Hi, I'm Brian Bonlander from NCAR. I'm just trying to learn some of the terminology you're using. I'm curious, are there non-exploitation platforms, or what is the term exploitation supposed to communicate?
To me, exploitation means that you're able to really take advantage of the Earth observation data that's on that particular platform. I did start to develop a matrix of these different components of like what makes up an exploitation platform according to the sort of common architecture. And one thing I found is that there's a lot of example notebooks out there that you could run on something like MyBinder, but that's not an exploitation platform, right? Because you're not able to take full advantage of the data when you don't have a data processing backend, for example.
Okay. Thank you.
One more question.
Anybody else? No more questions.
Cool.
Thanks.
All right, thank you.
Okay, next we have Clement. He's doing this from Europe, so we're just going to switch that around. All right, Clement, you should be able to share your screen now. Say hello. Let's make sure we got an audio.
Hello,
feedback.
everybody.
All right, we can hear you. Excellent.
Good. Wait.
All right, we can see your slides now too. Excellent. Off you go.
Good. Hello, everybody. I'm Dr. Clément Albinet from the European Space Agency based in Frascati in Italy. And I will present you the use that is made of the multi-mission algorithm analysis platform, the MAP, for the biomass mission, and how we came a little bit, how we defined a little bit this concept in order to use it for the biomass mission. So the general context is that this biomass mission for ESA is the first P-band SAR that will ever be launched in space. So it's a very innovative instrument. It's the first time we'll build it and launch that kind of instrument in space. And we ask ourselves how to bring some innovation in the ground segment. So in the way we bring data to the scientific users, the way we interact with the scientific community. So first, we gather a little bit of lesson learned on the operation of R&D missions, like the biomass mission. So it's new type of sensor technology, new type of geoscience. There's a very high importance of flexibility of Calval, and there are consequences in the exploitation phase. We have to be ready for unexpected aspects, both with the sensor and with the data, because the first time we launched that we have that type of instrument, so we have to be flexible. We need a lot of reactivity. We need to be ready to exploit the team readiness and imagination. The improvement of the processing algorithms is a key point, not only during the commissioning phase, but during the whole duration of the exploitation phase. And here we need a lot of collaboration. We need to be open, transparent. We need a lot of traceability for the in situ or the reference data, for example, for the way the algorithms are defined for the documentation in general. We have to be ready to explore new products, especially those associated with the secondary mission objectives, because we have new type of instruments. So we usually define some core or main, let's say, mission objectives, but scientists, the scientific community comes with great ideas, and we have to be ready to catch these opportunities and to work with synergies, sometimes with other missions or with some communities that we didn't involve at the beginning of the mission. And in general, we have to be ready for scientific discovery with the data product during the mission lifespan. We also ask the scientific users what were the issues today. And the issues were always the same for almost everybody. How to share my results, sharing like 10 gigabytes. 10 gigabytes is not a lot. We have Sentinel-1 images that are around 8, 9 gigabytes, but it's difficult today. It's not that easy to share 10 gigabytes. It's not a lot, but it's not that easy. If you want a free service to share 10 gigabytes, sometimes some users don't know that they're using the latest version of data set. They sometimes complain to us that there are some issues, and we tell them, hey, look, we solved that a while ago, and you are using an old version of data set. Sometimes they want to do things that are not allowed by the toolbox that we provide. Sometimes the computation take a lot of time. Sometimes they don't like, let's say, the official data that we provide, and they have good ideas to improve it because they are specialists in this domain and they have different point of view on the things. They're spending a lot of time to handle terabytes of data. If you're working with Earth observation data, you spend a lot of time to copy data on hard disk. You need external hard disk. You need to back up this disk. Sometimes the disk are lost. You can lose some data sometimes. It's a lot of effort, and it's a kind of job that IT people are doing much better than scientists. It's not really a scientific job. And sometimes they want to know where to find in situ data that are needed to validate results. And usually this in situ data is rarely open. And people are more and more demanding because the information technology are changing quickly the behavior of people. There are streaming services, for example, music and video. People can access directly the part of the information they want. They can continue to watch the movie exactly at the point where they finished last time. They can start a new movie without waiting to download the whole movie, for example. They used to have active collaboration, like Wikipedia, TripAdvisor. People are willing to share information with the community. They're willing to spend some time to share their knowledge and help the community in general. And there are some passive collaboration through crowdsourcing, like the road traffic information. You use the application and you contribute to the application just by using it. And in general, people are benefit for people is to get more information, faster information, or cheaper information. And another issue that we noticed is that usually the different services that we're providing to Earth observation users are quite scattered. So we have a website for the data access. We have another website with the information on the mission, web page, wiki. Another information where you can download, another website, sorry, where you can download the toolbox. Another website where you have tools that helps to support the processing of the data, like virtual machines. Another website where you find reprocessing service. Another website with some training. Another website with the forum. And sometimes the users are a little bit lost and they don't even know that some of these services even exist. And in general, users not only want better services, the way we provide them, but they also want additional services, additional functionality. They were requesting the possibility to access algorithm source code used to generate the mission data, to modify them locally, the possibility to execute large scope processing or reprocessing, to self-validate the results, and to propose new mission algorithms. And to answer to all of these different, let's say, service in a better way, in this new functionality, we decided to work and to define this concept of virtual research environment that we call the mission algorithm and analysis platform. So for the scientists, the benefit is that it enables researchers to easily discover, process, visualize, and analyze large volume of data. It provides tools and infrastructure to bring data into the same coordinate reference frame to enable comparison, analysis, data evaluation, and data generation. It provides a version control science algorithm development environment that supports tools, collocated data, and processing resources. And finally, it addresses the intellectual property and sharing issues related to collaborative algorithm development and sharing of data and algorithms. How does it look like? We identify different type of users, let's say, type of use cases, type of users. So the first type of functionality are related to data visualization that we aim at providing to all the type of user, even, let's say, the great public, with 2D data visualization, 3D data visualization, because for the biomass mission, we'll have 3D data at continental scale for pulsar or tomographic data, the possibility to generate time series visualization, to visualize the in-situ measurements, and additional external data, like meteorological data. For, let's say, Earth observation experts, so a little bit more expert user, the possibility to select different algorithms, all the version of the official algorithms, or other type of algorithms, derived version, to generate the products on demand, on the fly, maybe, to download the data, to upload data on the platform, and to share link to give access to the data, export figures, or export embedded content in web page or from PDF. And for, let's say, experts in the mission, the possibility to access the source code of the core algorithm, the official algorithm, to modify them locally, to generate the corresponding product, to validate the data, because we provide the tool for the self-validation, to create figure, to share the algorithm with other users. And the idea is to provide a free access to all the functionalities with a limit of processing time and data storage. This is under definition, knowing that additional resources could be ordered or allowed for specific users. We could make an AOs, for example, to provide additional resources. The idea behind that, the way we plan to use these functionalities for improving the core mission algorithm, is to start with a first definition of the algorithm, a first implementation of the algorithm. The user will have the possibility to access the source code, to modify it locally, to generate locally, the corresponding new data set, have access to the tool for self-validation with the in-situ data, everything. If they're happy, if they see that it's an improvement compared to the baseline, so the official algorithm, to propose, let's say, their update to be part of the new algorithm. There will be a verification and approval by ESA of the new official data set. And then this modification will be included, like a pull request that will be accepted, will become part of the new, let's say, official algorithm. And this is quite easy because these three big boxes are made within the map. So processing algorithm evolution is easier because the development and the implementation are made within the same environment. We plan to generate the level 2/level 3 product directly within the map. So we don't need to have a, let's say, a painful transfer to operation into another infrastructure. It will allow to write faster to stable algorithm, which is quite important for R&D missions, using a cooperative approach, because any PhD student, any scientist, even outside of the core science team, can contribute to the algorithm. And this is very well adapted, this concept of open science, to R&D Earth observation missions. For the first implementation of the algorithm, we put in place the BioPal open source project. Here also it's a new concept. So for the first time, we open some mission algorithm in open source way. Today in the BioPal, you can find the prototype algorithm of the level 2. In the future, we'll add the level 1 as much as possible, because we still have a few IPR coming inherited from reuse from previous missions. And the level 2 and level 3 fully, open source, and will be provided within this BioPal project. We plan also to add additional, let's say, relevant algorithm, for example, related to secondary objective, like a digital terrain model or other type of processor that will come in the future. In the map, you will have also all the functionality related to information sharing, like a forum, like a web key for interaction between the users and the agency, linked to social network, and possibility to extend through notebooks that are a very nice way to have an interactive information. Open science is extremely important for us because it allows collaboration, it creates some beneficial synergies, it improves teamwork, it encourages both higher quality of work and community feedback on the work. Anybody can find issues on the work you are doing. Work has a greater impact across the scientific community because people can reuse part of your code, so can check it, can reuse it, and can build on top of that. It creates new opportunities to leverage data resources, and finally, it encourages reuse of algorithm and computational workflow, which leads to greater reproducibility. As a conclusion, the map will make the connection between the data, the algorithms, the software, and the results. It will bring together data from various spaceborne missions, from various organizations, to support the development of global biomass maps. The objective in the longer future is to create global biomass maps, not only based on the biomass mission data, but also including NISAR and GDI data, using the best of these three missions. BioPal and the concept of product algorithm laboratory will make it easier to reproduce results and build from existing works. And finally, the concept of map will become the baseline for all the future ESA missions. So we plan to integrate it on all the future Earth Explorer missions, like Flex, like Harmony, if the mission is selected. It will really become the baseline for all the future missions that we'll have at ESA. Thank you. Do you have any question?
Thanks, Clement. I think we have time for one question, if anybody has one. Okay, I got it.
Hello. This is Brian Bonlander again from NCAR. This is not the first talk I've seen about I guess you'd call it almost like a laboratory for algorithm development. And I tend to hear about them once or twice, and then I never hear about them again. So I'm curious if you are aware of these other efforts in the past, and if you feel like your platform is different somehow.
So I'm convinced that our platform is different here. So in the past, indeed, there were some example of platform allowing, let's say, code edition, for example, but they were quite limited sometimes to very small, let's say, scientific community of or parts of some missions. Here, we really build the platform in synergy with the mission. So we'll have most of, and in the longer term, all the mission algorithm that will be completely open. We really use the platform to be the main interface between ESA and the biomass mission community. So that's something extremely important for us. All the evolution of the algorithm, especially level 2 and level 3, will be made through the map. So it's something which is extremely important, and we believe that that's why it will work with this platform, because we're really used to interact with the scientific community, but also ESA will use it to generate some products and to improve the algorithm. So it's not only, let's say, a toy that we provide to the scientists to have fun and make some discoveries. Really, the agency will use it as the main point of interaction. So it's an important pillar of the mission.
Yeah, from the NASA side, I'll confirm, like Clement said, this has mission support at ESA. It also has support at NASA, long-term support, and we're expanding it. And I think a good indication, you're going to hear some talks, it's being cloned. So people are going to our GitHub, making new versions of map. So we've already created the ecosystem. It's got a life of its own.
All of future missions, the community are requesting a map at ESA.
Okay, next up is Hokwa from JPL. He's going to talk about the architecture of MAP and also about the interoperability and open science aspects.
All right, everyone. Now that we've heard both Amy and Clement talk about the higher level aspects of these platforms, as well as the science-specific use cases, we're now going to dive in a little bit more about the design elements behind MAP, the architecture and aspects of interoperability and open source science. By the way, I'm presenting on behalf of the broader MAP team here. We've actually got many of the MAP folks sitting here as well, across JPL, Marshall, Space Flight Center, Ames, University of Maryland, and ESA as well. Oh, there we go. All right. So we wanted to first start off with just showing this. This is actually a screenshot of two press releases. On the left, you have a press release on the NASA side, and on the right, you have a press release on the ESA side. What's interesting about this is that it kind of shows that not only, as Stinger was saying, it is a joint collaborative effort, but it kind of raises lots of interesting questions from design and interoperability and architecture about like how much of this should be shared, how much of this is common, how much of this should be unique and distinct between ESA and NASA. And I think those were some of the challenges that we were looking into. And I think at the start, to kind of help answer some of these questions, you might always be wondering, why do we call it MAP with two A's? This sounds like a sheep thing, doesn't it? So it actually turned out that originally, as similar to what Clement was alluding to, it was originally called the Multi-Mission Exploitation Platform. I think it goes back to that question about what's this exploitation thing? And I think it has a lot of heritage to to, many of you have heard, right? ESA has a lot of exploitation platforms, probably more than a dozen, but they do various different discipline-specific, discipline-focused analysis capabilities. But what we did then is during the early formulation years of MAP, we called it the MAP, the analysis platform. But quickly, I think what was discussed was that, as Clement was saying, right, there was a focus on the ESA side to support rapid algorithm development, high iteration, product generation. But then also on the NASA side, we also had an additional, emphasis on analysis and on-demand analysis, and the interactiveness of it. So I think it was over a fateful dinner in Rome one year. It was probably too many drinks, but it was decided to call it MAP, right? And I think we had George there actually created a logo with a sheep on it too. That was our early MAP icon there. Anyways, this is kind of like why there are two A's in MAP, and I'm bringing this up for a reason, right? There's emphasis and there is design aspects to that. And I think one of the key things that we were trying to stress is that we're trying to solve many pain points here, right? We're not going to solve everything, but one of the key pain points that we saw early on, I think it's one of the ones that Clement listed, was that on one hand here on the left, we have production systems that are generating massive amount of data, but these are typically what we know as standard products. But then on the other end of the spectrum, we have science teams, algorithm development teams, and they are developing algorithms. They are iterating on the algorithm development process. But there's a gap that how do algorithm developers have access to the same large scale production capabilities that on the left side, these other teams have. And so in a sense, what we're trying to do is bridge that gap, right? And it starts with having a shared algorithm catalog. I think it goes to the heart of that question again about what is different here. I think what it's uniquely different here is that how do we provide an integrative environment that not only lets, on one hand, the algorithm development teams develop their algorithms, but support what we call improve the time to market. How do we take that algorithm and provide fast access to deploying that algorithm into a production system to generate products at scale, and then to iterate on that repeatedly. But to do it in a way such that the same algorithms through these purple arrows here, it's the same algorithms that are actually being used in the production, as well as the higher order transformation, right? Like, so for example, generating level 3 products, level 4 products, and then integrating them in a way that is a lot more analysis ready, right? Like ARD products or even analysis optimized data services, right? How do we bring them into fruition so that we can conduct analysis? And the key there is through these blue arrows too, that there are interactive aspects in an algorithm development environment. How can we interactively engage in the processing, the transformation, the analysis? And finally, how do we repeat the process? How do we assess, iterate, and improve and automate all of that? Another example, a little bit different from what Clement was showing. This is one from Marc Laval at JPL. He's actually been doing a lot of SAR analysis work, and here this is an example from him showing how he's using the map to do applied above ground biomass using Sentinel-1 SAR imagery data. And what's interesting here is that it kind of addresses many of the goals, right? How do you access the data? How do you do rapid algorithm development? How do you do analysis? And one of the key takeaways is part of this analysis requires a massive amount of data to be processed, generating a co-register SOC stack. But how do you do that repeatedly and interactively in an algorithm development setting is really one of the key pain points we're trying to address here. And I think just to kind of showcase some of the architectural philosophy behind this, it's about how do we provide an algorithm development environment that allows algorithms to be built, so to speak. Imagine it's a container, right? An overglorified container, but to take that same container to be the thing that is used to register and deploy for generating products rapidly. And then we would then catalog and generate the same, the usual SDIS data cataloging, support for not just cloud optimized data sets, other things like ZAR and other data stores, but also how do we fold in access to data, right? Not just NASA data, but also ESA data. But do it in a way where we could iterate, so that we can actually access the data for further analysis and then repeat the whole process, right? And do it in a way that I think you're going to hear Kaylin's team there. They're going to talk more on the data side. They're going to get a more deep and more depth about some of the data services. But the overall idea is that the results that are generated are equally accessible from the same algorithm development environment. So effectively, the algorithm development environment is the environment for not just doing development, but it's doing the analysis and the iteration and the control plane for the actual development and product validation and product assessment itself. And so at the end of the day, if you take a step back, what's on the left here in purple is really focused on algorithm development, and what's on the right here is focused on the analysis, but it's the same interface, it's the same system. That's really what was distinct about this. You know, from a user's perspective, they're interacting from the same fundamental interface. I'm not going to get into depth about this diagram here, but the overall idea is that we've identified early on the very top there, you can kind of see in the top that there is an ESA element there. It's actually all you see is my face, but there is an ESA element behind my face that we're interacting with, and we have a shared code repository. So we're basically we've identified joint services between the ESA side and the NASA side, as well as a joint NASA CMR for all the data cataloging. But within this blue box here, we have the NASA side map. So these are the areas that are unique to the NASA site map. And we've identified through these larger boxes like key element, key service areas, like service areas for doing algorithm development that the teams are going to get into more depth later. Sujin's going to show a lot more of that later. And then we have the data team showing like their visualization, the data management services. Sujin's going to talk a lot more about the data processing service. But the idea here is that we've identified common elements as well as common services that provides a lot of the backbone foundation, including authentication and authorization. But we are reusing a lot of elements here. So we're using same systems that are used in NASA SDIS DAX. We're using same science data processing by the NASA missions. And we're reusing like the COVID-19 dashboards that Amy had actually, she didn't talk about it, but her team has been doing a lot of effort on that. I'm not going to get into detail of this because I think Kaylin's going to cover this and we're running short on time, but there are layer architectures behind this that Kaylin's going to get into. One of the key things we want to convey is that what is different, right, about how we're doing algorithm development here. We are trying to represent artifacts of this across different life cycles, from where it's in a code repository to where it gets manifested in like a Jupyter notebook to where it gets deployed into an executable. And we basically identified the map services that are bounded to it. We have the algorithm development environment that checks the code in and out. We have a catalog that is cataloging searchable artifacts of those. And then the key here is that we have processing clusters that are actually registering those algorithm artifacts and running them at scale, generating those products. In terms of open source science, though, we're trying to answer certain questions like, can we enable collaboration? Could the same algorithms in MAP be used on like an ESA exploitation platform? Could an algorithm from the ESA exploitation platform be used in MAP? Could we process this not only in Amazon? Could we do it on, say, high-end computing or Azure or Google, for example, right? So it turns out that we don't really need to reinvent the wheel, right? I think Amy alluded to this earlier. OGC has defined international standards, right? And OGC is a standards body. They have weight, right? But it turns out they've defined specifications for algorithm specifications and workflows and processing and different API processing, as well as orchestration through common workflow language. And what we've done is basically say, you know what, we've identified common elements, and we could basically leverage through these purple font elements where using those OGC standards as an interoperability point, we can actually use that to enable a lot more homogeneous service interfaces across the ESA and NASA map, where we could have processing elements that could also, via these OGC standards, homogenize the way that we represent an algorithm unit to how it gets deployed in Amazon to be equally the same as how it gets deployed, say, even on high-end computing. So in a sense, what you see is that in the center there, we've identified services that are actually jointly shared across the ESA and NASA map, but at the same time, on the NASA side and the ESA side, we have services that are effectively co-located. For example, map services on NASA are co-located with the NASA DAX. But part of that is that, there's a data locality issue, right? Certain services are closer to NASA data and certain services are closer to ESA data. So we are trying to address these egress issues, right? Moving data from ESA across to NASA and vice versa. There are, we're looking to like requester pays as one of those key things. And got 2 minutes, I'm gonna talk about this real quick. So we have, we're also been expanding across into high-end computing. And so in essence, can we take the same algorithms and deploy them to run at scale also onto high-end computing? And this is just an example of tile generation that Laura Duncanson at UMD has been applying on the MAP project for boreal biomass map generation. The idea is, can we take the same tile generation and run them on high-end computing? And one of the key emphasis points here is that when we look at the broad landscape of cloud, there are different cost models. Amazon, Google, Azure, and NASA Pleiades, for example, they have their pros and cons, right? There are certain aspects that they excel at. Certain cloud like Amazon is actually not the cheapest in compute, but maybe Google is cheaper in compute, but NASA Pleiades is free for a project to use, for example. And when we look at data locality, NASA has all of the data in the US West 2 Oregon region. So we have to factor in egress cost aspects to this. If we were to process, say, in NASA Pleiades, we need to move data out of the cloud in Oregon and move it physically to the Bay Area. So these are some of the things that we're looking into. What's interesting here is that when you look at processing, it's just one example using Sentinel-1 data. On Amazon, it actually is quite expensive relative to, say, Google. Google is cheaper on per unit of compute. But NASA Pleiades is free for the project, but it takes longer because they have relatively slower instances. But when you look at the fact that we have to move data, it starts getting quite interesting because Amazon has a home field advantage since we're in Amazon, right? And by factoring all of this, we can actually do some assessment that, wait a minute, it's actually quite expensive to process certain workloads in Amazon, but it could actually be cheaper to move data out of Amazon into Google and Azure to process, even factoring egress. But when you look at Pleiades, it's actually cheapest, because, or at least to the caveat that there's no cost to the project, right? We're actually paying for egress to move data out of Amazon. So that's kind of like one of the premise behind why we want to expand MAP into also supporting high-end computing, but doing in a way that is commensurate with all these OGC standards. And ESA has expressed interest in doing similar. I'm not going to get into details of this, but the idea was just that OGC has defined standards for us to enable a lot of that. And I think Amy alluded to earlier that part of the standards, including how do we represent a job, a distributed algorithm to be manifested as a job, but in a way that supports things like stack, and S3 axis and things like that, and to represent in a way that constitutes a stage in, process, and stage out. And the key takeaway is those notebooks that people are interacting with, they get embedded as the processing step behind that. We're now looking into things like Streamflow as a way to decouple, and I'll get into this, decouple the orchestration from the execution. And that's really the key takeaway here, is that we're looking at that decoupling so that users could define their workloads once, but by decoupling, we could then deploy the algorithms for product generation onto, say, NASA Pleiades or Amazon, whether it's Kubernetes or even HighestDS or Amazon Batch for that matter. And these are just examples of how we're trying to optimize behind that. And let me close with this one last slide here. One of the things that we're finding out, and this is really driven by our partners at Ames that have been doing this for years, but what we found is that it's actually quite expensive in compute in waiting for Amazon S3, right? It's something that you really don't think about on a day-to-day basis. S3 is like cloud, right? It's fast and scalable. But when we're really optimizing, in Laura Duncanson's boreal biomass example, she's doing 10,000 job runs, 1 hour each. So let's say 5 minutes out of every job is spent loading data. That means that for that 10,000 hour run, we've wasted $600 doing data movement alone, and we haven't really leveraged those CPUs. So by optimizing the stage in and stage out, say by moving the stage in, stage out onto lower cost compute, we could actually do that same scenario instead of spending $600 just waiting for data to move out of Amazon S3, right? The really fast storage, but it turns out that it's not fast enough if we really optimize. And so by moving it to, say, a T2 micro, we could spend $29. So I'll just end with that. And this is just the key points that I've presented.
Thanks, Hook. Time for a question. Valerie.
Hey, thank you. Valerie Dixon, NASA ESDIS. Hey, Hook, I wanted to go back to the diagram you had of shared and co-located infrastructure. I wanted to ask if the co-located infrastructure, if that was shared equipment and deployments, or if they were also redeployments, how that was being managed.
You mean for the shared part or is this the slide you were talking about?
Yes, this is a slide. So the co-located, portions, are those the same as the DACs are running, or are they redeployments of their
Great
software?
question. For the CMR, we're actually using, as Doug knows, we are using the NASA CMR. There's also a copy in MAP for some of the non-standard products, and I think there's some interesting discussions, especially Doug trying to bring up how much of that can we move fully onto the NASA Estes CMR
Yes,
as
yes.
an optimization.
Yeah, no, and I know that there is a MAP CMR versus an EOS CMR, but I was wondering about the other co-located assets, and on the left side and the right side for ESA as well. If those were also MAP deployments of those components, or
They are, like, for example, the data, actually, Suj is going to talk about that one, but the data processing element is co-located with the NASA DACs in US West 2 region. So that all of the processing is right next to the NASA data. But ESA has their own counterpart. They have their own processing element that is co-located with their ESA assets.
Thank you.
All right, we need to move on. Kaylin? We'll talk afterwards. Kaylin's going to give us an overview of data stewardship within MAP. Did we give Hook a round of applause? I don't think we did.
Which one is it, Doug? Is it on your own? Stewardship.
It's just a space bar. Yeah, I'm trying to go to the, here's the speaker. So, and then just let's make sure you're in the visible mode. Yeah, looks a little bit. Okay. Thank you. Okay, thank you. Hi, everyone. My name is Caitlin Bugby. I'm from Marshall Space Flight Center. It's my honor to present some of our work on behalf of my amazing team. You can see the list of people there, and Aaron, who's my major co-author on this presentation. Today I want to talk about data stewardship in the MAP, and if you're not aware, today is the anniversary of the Apollo 11 moon landing, so I had to give us a fun title of One Small Step for Data Stewardship, One Giant Leap for Users. So I'm going to be talking about a couple of drivers behind the MAP. You've heard a lot of different perspectives on that so far. I'll just briefly touch on the MAP data system, but I'm really going to be focusing on stewardship in the data lifecycle in this presentation. And then I'll hit on some lessons learned and next steps for the project. So the first driver, as you've heard from Clement and others, is open science or open source science, really looking to enable that collaborative culture with technology that we can empower sharing of data and information and knowledge. So the MAP is really built to accelerate sharing and to make research more efficient by enabling science at scale, which you heard from Hook a bit there. So we really want to reduce the time to scientific results by making things more efficient for scientists and really enabling that collaboration. But I think the other driver from my perspective is these cloud computing cyber infrastructures. And as we've heard, these provide scalable on-demand access to compute with data co-located. And as you know, many organizations are moving to the cloud to really take advantage of that paradigm, but we are in a period of transition. So some data is on the cloud, some is not. People want to run analysis at scale, but not all of that data is available on the cloud. And we're still having a lot of conversation in the community about what are the best cloud optimized formats, what are the best analysis ready formats. And so in this period of transition, I think, MAP, we're really trying to work to help users get through this transitional period. So from my perspective, I'm thinking about what do these drivers mean for data governance and stewardship? And what's our responsibility? How do we care for data and information in an environment like MAP? And what does the data lifecycle look like? And what can we do to make using data easier for our community? So just really quickly, I just wanted to show the map data system architecture. As Hook mentioned, we are reusing open source data system components from ESDIS. So we do have our own instance of the common metadata repository for discovery. We also have our own instance of the Earth Data Search client. But supporting the stewardship process, we are using Cumulus and the metadata management tool for metadata curation. So just wanted to highlight that. If you're interested in having a more technical data system presentation, just reach out to me. I'm sure Amy would be happy to provide more details on the technical side. Okay, so I want to talk about the data lifecycle in MAP. And so just at a high level overview, it looks something like this. So first, we need to identify data to include or connect to the map. Next, we take a look at the data, we profile it to assess the level of service that needs to be provided for that data. Once we complete that, we curate and onboard the data. And then if we've decided that we want to provide that higher level of service, we optimize the data. Then, of course, we monitor the data for new versions and deprecation as needed. I will say this is kind of inspired by, you have your traditional data lifecycle, but there's also this movement in enterprise services at looking at data governance. And really, the MAP platform is more of this holistic ecosystem. So really looking at what does governance look like in this environment. But before I go into a little bit more detail about each step, I just wanted to acknowledge the roles that our team plays in MAP. And we heard a little bit about this from Rebecca yesterday in the plenary, that there are very few unicorns in data science who can do everything. And so we have data engineers like Amy and Chuck who really help us bring the data in and make it discoverable and accessible. We have data stewards who make sure that we're curating the data, providing the right level of metadata, and assigning that level of service. And last but not least, we really depend on our project scientists like Clement and Laura Duncanson, who really help us identify relevant data and make sure that we're transforming that data in an appropriate way. So together, we make a team that really makes this work well for us. So just walking through the data lifecycle, I'll just start with identifying data. When we started the project, we had something like 80 data sets that were identified as relevant, and we constantly get requests for new data sets to be brought in. So we wanted to move to a more responsive way of identifying data. So we've implemented a form where our scientists can request new data, or they can upvote a data set that's already been requested. We take a look at that, just double check and make sure that data is not already in MAP. Take a quick check to make sure it's scientifically relevant, and then we do a feasibility assessment. So we're looking at how challenging would it be to make this data available in MAP, and that looks at cost. Is the data openly available? How complex will it be for us to bring that in? After we've done that, we've identified the data, we've done a quick look at the feasibility of bringing it in. We then look at profiling the data. And we were really inspired by the level of service model worked on by some of our colleagues to prioritize data ingest and services. And this is really acknowledging that we have finite time, and so we really need to prioritize which data products receive a certain level of service. So we do this through service level assignment based on data product categorization. And we do that by a number of dimensions, including the type of data, the data producer, data quality, et cetera. So while this is something that we have to do now, given our finite resources longer term, we do hope to really build workflows and components that enable the same level of service for all data. Here's a sample of the assignment matrix. I can provide more details if you're interested on how this works, but we're looking at the standard is kind of a basic level of service, whereas like comprehensive, we work to optimize the data for the cloud. So I'll show a little bit more about that later. So once we've assigned that level of service, we're ready to curate and onboard the data. So if the data is not available in the cloud, we curate collection level metadata along with some additional attributes I'll talk a bit more about. And we also curate granular metadata. We run Cumulus to bring that data into the MAP data store. And then we just verify that everything was brought in properly, complete, and accurate. One of the things that we did for this project is we saw a need for expanded metadata information. This came out of our science use cases to support some unique search criteria. So in collaboration with ESA, we developed a number of these additional search attributes. And they fall across a number of categories, including SAR, LiDAR, and in situ field measurements. You can see a little bit there. And here's some more specific examples of what those look like. We have about 40 that we've enabled. Thanks, Doug. And they're applied at both a collection and granular level. And we have these querying services that allow users to really take advantage of that information to search for things like the site name of a field campaign, which can be really important. When the data is available on Earth Data Cloud, we are smartly connecting to that. So as you may know, some of our science data is migrating to Earth Data Cloud, and so we want to take advantage of that. So whenever we can, we do that, and we replicate metadata to enable discovery of that data within the map. This is a similar process there. I won't spend a lot of time on that, but after we've brought in the data, for the data that received a higher level of service assignment, we do want to work to optimize that data. So we've been working on providing a number of innovative services, including fast browse, subsetting, and structured data stores. So what we've prototyped is providing the cloud optimized formats as a separate collection. Talk a little bit more about that. And if you want to know more about the dashboard that Hook mentioned earlier, just let us know. So one thing we wanted to try was curating the cloud optimized data as separate metadata collections. We went with cloud optimized data because there's still a lot of conversation in the community about what analysis ready data sets are. So we thought at the minimum we could optimize the data for use in the cloud. So the map connects people to the official science products, but also to these cloud optimized formats. And we've provided them as separate collections and granules for discovery. And it allows us a chance to document any differences that may exist between the science product and the cloud optimized data. So as a part of that prototyping work, we also developed some best practices that we kind of learned from curating these cloud optimized data collections. Then lastly, we want to monitor data for new versions and usage, and also deprecate data as needed. So we do get some support from the project scientists here. They let us know, hey, there's a new version of this data set. We're really excited to work with that. So what we do now is we do deprecate old versions when the new version is tested and available in the map, and we let our stakeholders know. But longer term, we're looking at taking advantage of having data on the cloud and implementing a process that you can see there on the right with maybe leveraging some cold storage options just to see how that goes. We also provide a deprecated collection page in our user documentation to let people know, hey, this data set is on a new version, just trying to make sure that we're being as clear as we can with our users. So just really quickly, lessons learned. Since not all the data is on the cloud, we've really had to prioritize data ingest, as you've seen, given cost and time constraints. And so it's really important that you communicate with your users and make sure that you understand their needs and prioritize accordingly. So it's great having a traditional publication model because we get a certain level of quality and stewardship, but it can be a blocker. It takes some time. So if we have users who need something more quickly, it can be an issue, which is one reason why we implemented the level of service model and the data request process. And so, as you might imagine, cloud native platform capabilities are optimized when you have data available in cloud native formats. And we really lean on our subject matters to help us create and validate those data transformations. And these, as I mentioned earlier, these can be unique from your traditional archive counterparts. So that required the separate curation. And lastly, the clear documentation is really important. It really helps people start working more quickly and efficiently with data in the cloud. So just wrap up with next steps. Hook mentioned this already. We've been collaborating with AIMS on high-end computing, looking at Stack and OGC application packages. We want to look to support more generation of cloud optimized data. As more and more of the archival data becomes available, we can look to really put more effort into that and promote those stewardship practices around that. And lastly, we just want to empower our users to do more. So we want to bring, needed data into the system without blocking our users by this traditional publication model. We want to share data and code with the MAP community, along with the documentation to enable discovery, understanding, and more efficient use. So thank you for your attention, and let me know if you have any questions.
Well, you don't know this, but she finished on exactly 0 seconds. That is impressive. Any questions?
Hi, Rich Signal, USGS. I just got a inquiry from a colleague at USGS yesterday about, like, I'm trying to access some data from NASA thread server, and it's, and I'm trying to do it with like a bunch of compute, and of course that doesn't scale. Is this data available somewhere, else, like on S3 or somewhere at NASA? Like, how would somebody, where would you go with that kind of a question? Or is there a way to find out what data is in the cloud somewhere?
There is, and Doug may be the better person to answer that question.
Well, I should have been listening.
Basically, no, I can quickly answer it, and Doug can correct me what I get wrong. If you visit Earth Data Search right now, there's actually a filter that you can toggle on and off that will let you filter out data that's on AWS.
For that question, you got a map account, right? Yeah.
Kaylin's answer is exactly right. Okay, next up we have Sujan. He's going to talk about data processing at scale on the MAP platform.
Let's just make sure you're visible in that little square. Yeah, sweet.
Hi everyone, I'm Sujan Shah. I'm a software developer at Jet Propulsion Laboratory, and I primarily work on the map data processing side and a little bit around on the platform. So, I mean, you all have heard a lot about the map today and also seen quite the architecture, so maybe there are some slides that might be a repeat so we can go quicker. Well, as we all know by now, that we want to create this analysis framework where scientists can come on lab, work as a team, collaborate, and also develop the algorithm and run at scale within the same environment. So what does MAP provide? Provides all of these interfaces. So my work primarily and the team was in building these interfaces so that it's as easily usable as possible. So we've heard ARDs, we've heard DPS. What are these? The different elements of MAP. So one is the algorithm development environment. We primarily use this technology called Eclipse, that's like the cloud native IDE. And we've built our own custom kind of a Docker image for Jupyter Lab that includes extensions that allow users to interact with these different map services. So Jupyter Lab is the base that the algorithm developers would use for development. Then we have the next, which is the algorithm store that you heard about, where once a scientist is comfortable with their algorithms, they can use the map API to kind of register their algorithm using a certain interface, or basically a YAML configuration file that we provide. Once that's kind of checked, it goes to a CI, it gets versioned and published into this repository. The next part would be using the data processing service. Now this is where the large scale part of MAP comes in. We look at the algorithm store, pick out the executable container, and then run at scale. What happens behind it, we coming up in the next slides, and the glue part out here in our services is the map API. This is the one that's the OGC compliant API, and for the DPS part, we kind of support the web processing standards, or WPS, for being interoperable with kind of different DPSs. And then you have the analysis service that we had seen earlier. So what is the map data processing service? Underlying, it uses HiSDS for people who are familiar with HiSDS. It's deployed on Amazon. It uses auto-scaling groups. We use spot instances for kind of optimizing costs. And then all the jobs are kind of packaged as Docker containers. So the algorithm goes to the CI, as I talked about, gets packaged and deployed onto individual EC2 nodes running in the Docker container. What does this give us? This allows us to support different kind of programming languages or different software stacks for the scientists to use. So we are not restricted just using Python. You can run R. We have projects where you can use Julia. We've tried that as well. Or you can have a simple bash executable or C, whatever you're comfortable with. The other advantage of using kind of the EC2 or the HiSDS software is the user or the algorithm developer can choose what kind of compute they want behind. They can kind of customize the amount of resources they need, the CPU, do they need GPUs, the disk space, or any other parameter for compute resources. All of this is configurable, and then they can run on these provided resource queues, as we call it. Some other aspects of making it interoperable is that the DPS is kind of wrapped around with the map API, which provides an OGC compliant interface into running jobs, kind of polling for statuses, getting the results. The DPS is also integrated to pull data directly from like external sources. It could be publicly available URLs or even DACs that require authentication. So the users can be like, hey, I need to pull this kind of file from ChipoDAC or ORNL, and then the DPS would go in and pull all of them, make it available for the algorithm to run. It also provides kind of statistics, like job monitoring, how are my jobs doing? That's something I'll be covering in this slide, in later slides, for how we did the boreal biomass production. So I guess this is one architecture that you might not have seen before. It covers the DPS. So you can see on the very right that there's Eclipse. That's the development environment that enables collaboration between the different science teams. Multiple users can jump on in, kind of develop and refine their code, then submit their particular algorithm to the map API that does the CI/CD, builds the container, pushes it to the algorithm store. Once it's there available, the users can then go and execute their particular algorithm. It could be a single execution, could be a batch. They could loop over it, and that is what we call the custom on-demand processing that goes into this HiSDS architecture, which is connected and has this backend of auto-scaling fleets that are configurable for the user based on the resources they need for that particular batch. Once the jobs are done, all of the data is stored on S3. And this S3 is directly mounted into user workspaces. So no matter how much data you produce, all of that is instantly accessible once it's produced on your workspace, like a normal file system. There's no download. It's just you go and you view all your data, and then you can do any analysis you want. One of the examples would be of kind of the scale is, say if you were running on a single machine and your granule takes 15 minutes to process, with the map DPS, you could kind of do a world scale production with 1,000 granules, for example, in 30 minutes. I'll be now covering like a real use case that we did in May. Now this is covering the boreal processing. We had about 5,000 kind of jobs. These were long running jobs that needed close to 30 gigs of memory for doing their processing, and they were on an average about 4 hours. And these are some metrics. Now, I don't know, it may be too small, but you can see in those colored bars in the center with like the red, purple, orange, the different types of instances that were picked up. And this is again using the Amazon Spot fleet. So Amazon is kind of optimizing our costs to be like whichever instance is cheapest available in the region at that time. And then you can see the distribution of instances. And then we just have like the exit code and which algorithm was running. So this is an example of one algorithm in a pipeline of 4, and all of these 4 had been run for like all the 5,000 granules. So this is just the longest running one that you're seeing here. You can see like the distribution of the average time of all of these close to 4,700 jobs that occurred within 2 days. So that's the other thing. Now we have these jobs that are taking close to 4 to 5 hours, and we were able to process almost 5,000 of them within 2 days. And you can see the mean size of the outputs that they were generating. So they were taking in inputs from the previous steps and then producing small files of say 100 to 200 MB each. All of these 5,000 small files were then readily available for the users to see and analyze in their own workspaces. So this is kind of one of the key points of connecting the algorithm development environment directly to your data processing, and the users within, I would say, a month of developing iteration were able to run this whole pipeline of 4 different algorithms with 5,000 granules each. And then the longest one just took 2 days to complete. So some of the key features, you can see there's a distinction of how DPS tries to process jobs versus how you would have Xarray, for example, or something like a Lambda, that you can just have short time jobs with like a particular cap on resources. It's also a little different than submitting a map reduce function in a job. So the DPS would enable the user, or it sets itself apart by allowing user to just write an executable, use any stack, provide that custom stack, register it as an algorithm, and just run. And like you heard before, this core technology, HiSDS, has been and is being currently used in the science data systems for large Earth science missions like SMAP, OCO2, NISAR, SWAT, and OPERA. Well, and in the future, like Hook mentioned, the new MapHEC project, or the high-end computing project, wants to use this OGC compliant interface that I talked about to enable users to kind of submit jobs directly onto high-end computing platforms and Amazon, and kind of mix and match based on whichever is better for their use case. Some of the references of what I spoke about, all of the software is open and available on GitHub. And thank you. Any questions?
We have time for a couple of questions. Anybody? Amy.
So I know they did one big run in like September or October to generate the initial product and then the second product. So what were there important changes that you made to the DPS system between generation of both products that made it, I don't know, faster, more performant in the second iteration of the product?
So I think we learned a lot about the key failures in the DPS. So like Amazon sometimes will pull the plug on Spot instances when they're rebalancing in a zone, or if you're not using the right type of instance types in your fleets. So one learning was to optimize not for cost, but for capacity. So when you were doing cost optimization, we saw that in these long running jobs, especially, like you don't want to get cut out at like, at 90% of completion. And that's something that did happen a lot in the first run, a little bit in the second one when we realized, we could instead optimize for capacity. And I think that kind of helped us in reducing cost. And also some other realizations about how much hidden costs you can find when you're running at a large scale. Apart from configuration, I think in terms of, I guess, the software itself, it was pretty much set from the first run and the second run. We didn't change much, but the optimal config was one of our biggest learnings in the first and the second run, and how to save cost.
Any other questions? Okay. Got a cluster over here.
Hey, this is Haidian from Justice. About the algorithm, if it doesn't follow the OGC API format, is that possible? Like if the algorithm is very specific to some, the intrinsic details or like the data formats itself, they have additional parameter which is not accepted by the OGC standard. Is that possible to implement it in map?
So the algorithms itself are kind of Dockerized, so they don't need to follow the OGC spec. It's just the submission. So if there are certain parameters, like you're saying, don't follow the OGC spec right now, I think we may need to work on that. But if we support like JSON, for example, as an input, in terms of data types that you're saying, the data types are downloaded directly. I'm not sure if OGC kind of takes in data parameters as an input, but in terms of algorithm parameters, we support an entire JSON configuration file or strings or integers. I don't know what, apart from that, would you need to run?
That's very cool. Thank you.
Okay, yeah.
Hi, my name is Terrence. I'm from Azavia. You had a line in one of the last slides that said DPS has been tested to scale larger than Kubernetes. Can you expand on that?
So that's something I got from Hook. I think we've scaled in other projects and not Map particularly to over 8,000 nodes, is that right? On Amazon to run directly. And at the time, I think Kubernetes was not shown to scale up to 8,000 running nodes simultaneously. Yeah.
Okay, let's move on to our final talk. Hook is going to talk about some actual exploitation of this platform with image spec.
Oh, it's on a link. Okay. It's on the browser. Oh, it's browser. Okay. I'm sorry. I missed it. Oh, it's blocked.
You give access to that too. I clicked access on both of them.
While they're getting set up.
Stinger's going to give you 5 minutes of his best stand-up.
No, I just wanted to point out that Natasha Stavros is the PI of Image Spec, and Hook's going to be giving the talk because she wasn't available this week.
We could also share on the Zoom if we need to.
Sure. Hang on. Let me get you this.
Got it. Sorry about that.
Jim Call with CSIS. I was just wondering while we transition, is the ESIS model of algorithm development being ported over to Modus catalogs as an example for things like snow cover analysis?
You've stumped everybody. I rarely see this expression.
This is when I go, the staff?
Anybody want to field that? We'll take that offline. Hook.
All right, I will do this quick. I think as Stinger was saying, actually the main PI is actually Phil Townsend at the University of Wisconsin, but there's several players. Natasha actually originally gave this talk, but she's actually out on maternity leave, so I'm doing my best to fill in. I don't look like Natasha, but I'll try my best. Actually, this project here, ImageSpec, is actually a great instantiation of another map project, and we're lucky enough to have several common players in this across the MAP project and ImageSpec. In fact, Sujin is one of the key developers behind this ImageSpec project here, so it's actually been a great infusion success story, so to speak. All right, so one of the things that we're really trying to address in terms of what is this value proposition, what is this ImageSpec trying to do, right? We heard throughout all the talks today that there are a lot of key themes, right, that you're hearing, right? Open source science, right? Access to data, how do you do rapid algorithm development, right? And it turns out that in this field, this is actually the hyperspectral imaging spectroscopy arena, right, which is indicative of the upcoming ESO mission, the Surface Biology and Geology mission, the SBG mission, and ImageSpec, which actually is an imaging spectroscopy type of analysis environment in the cloud project. It's trying to address a lot of these pain points effectively. And you're hearing the same themes all over again, but unique to this domain here is that in this field, there are a plethora of algorithms, there are a plethora of competing algorithms in the open source, there's great collaboration, but how do they get access to all of this capabilities, right? And how do they get access to the data? How do they get, and so that's what we're trying to address here in terms of the value proposition. And one of the key takeaways is that aside from that plethora of algorithms to try out, and certain algorithms are not optimized globally, certain ones only work well regionally, for example, but at the same time, how do you get access to not just the data, but how do you get access to deploying those algorithms at scale, like what Sujin was alluding to, and to try out these variations at scale. And there's just many of these type of examples. And I think one of the key takeaways that Natasha here really wanted to say was that we can't do this the way that we used to, meaning that historically we depended on a single project to do this. But could we diversify, could we free up MAP, so to speak? Could we deploy other instances of MAP so that other projects could actually leverage its capabilities as well? And especially on the data access and the algorithm development aspects as well. I think this is almost like a marketing chart here, but it's kind of like, addressing the diversity and inclusion and all the open source, check boxes, right? But I think that goes to the heart of it. And I think this is an example here that we were trying to convey. ImageSpec is not only dealing with remote sensing data, it also deals with airborne campaign data. So it's even more important that we have an analysis environment. And I think this, checks off all those map boxes that in terms of access to data, how do we include in situ data? How do we include ancillary data? Access to remote sensing data, right? How do we do it in a way that is, people can search for the data, people can try out their algorithms and do their what if scenarios, but do it rapidly at scale and then iterate on the analysis results. What's even more interesting is that in this field of hyperspectral imaging spectroscopy, the data is actually extremely large. And so even larger than NISAR, for example. So how do we do this more efficiently? I think this is why having a platform like MAP is enabling a lot of these, these capabilities. And so it kind of goes to the heart of the key objectives here, why, ImageSpec chose to adapt MAP to deploy a lot of these things. And especially this word, on-demand processing, right? How do you take these algorithms to deploy and do on-demand analysis, both in terms of like this bulk analysis? An example here is in the above campaign here, how do you reprocess rapidly all of the flight campaigns from each, from these scenes here, these flight paths, but do it in a way where you can tweak an algorithm, reprocess all the flight campaign, flight lines, get some results, look at the results, and then go back to the algorithm and retweak it and regenerate this and do it rapidly. This is kind of like the key pain point. Sujin actually showed a similar slide here, but that kind of goes to the heart of how do we democratize this capability so that it's all more to the power of the user's hands, right? Like we said before, historically, it's the flight project missions that have access to this large-scale processing. What we're trying to do is, can we bring that capability more into the user's hands, to the end user's hands, so that a science team member or an algorithm developer could do this themselves? That's really, really what we're trying to do here. And here, I think Natasha really was trying to convey here is, what are those key things that the science users are typically doing, right? And I think a lot of this would resonate with us, right? We've heard this before. It's like, what do they spend 80% of the time doing, right? It's like mundane things like dealing with interfaces, whether it's with registries or data or GitHub, right? How do you deal with open source? How do you deal with the mundane things of data wrangling, right? It's how would map, for example, or this type of platform environment really lower the bar for dealing with these things. And having this end-to-end platform environment really helps to address, or at least check off many of these boxes here. The image spec system itself, it should look a little bit familiar because we kind of showed similar diagrams in MAP. Is because effectively image spec was an instantiation of a lot of the MAP services here. One of the things that we looked at early on was that we wanted to fold in other focus analysis platforms like Amazon Athena. We looked at Apache SDAP. But what was interesting is that along the way, we realized that a lot of the analysis capabilities that users wanted to do inside Jupyter and inside MAP's Eclipse Shade, they can actually do a lot of those capabilities already. So we kind of de-scoped a little bit some of those other capabilities, maybe for some future work. But the same algorithm development environment and the same large-scale processing holds in terms of what Sujin actually presented. We leveraged the same Eclipse Chain algorithm development environment. So the user experience, I think like what everyone's been saying today, is that users are interacting through the context of a Jupyter-like environment, and they're doing everything with it, right? It's not just algorithm development, but it's interacting with the analysis, the large-scale processing, and everything else with it. And this is just an example here of the different kinds of things. Unique to image spec here, a lot of the folks here actually are using not just Python, but RStudio, right? Like what Sujin actually mentioned earlier. Some of those RStudio algorithms, maybe even Julia, are built and deployed in the same way across Amazon. So it's almost like they are in different layers of abstraction. But the point is that it enables users to support different languages of their choosing. We actually embedded, if you look kind of carefully, this is actually Earth Data Search Client running in a tab. And this is something that the MAP project kind of pioneered in terms of Jupyter Lab extensions to embed additional capabilities so the user experience is a lot more consistent and more homogeneous and a lot more smoother, so to speak, in terms of not having to go outside of this algorithm development environment. But here you can see that in the image spec project, we actually catalog above hyperspectral campaign data so that users could actually search for it. And this is actually data generated on demand in bulk in the environment, and it's actually cataloged and shown and discovered all within the same environment. And here is another example here that shows custom algorithms that the users are developing, and they're able to register it into the system in order to run at scale and deploy at scale. And again, it's not just Python, right? It could be RStudio. And what's unique here is that on the upper right, this is like an interface to basically assess how your workloads are going. What's unique about it, though, is that in the flight project missions, the operators typically do this. But what we're trying to do here is, can we bring that power that we used to rely on the operators back to the user's hands so that they could actually do more of that? They have the power to assess that themselves, basically, so that there's much more integration. In this slide here, this is some of the more newer things that's going on. Natasha's actually leading this wearing her NSF hat. So she has separate funding that is moving forward and actually further integration of MAP capabilities, but trying to tie it in with, say, some of the Cyverse capabilities as well. And it's almost as though there is a movement towards democratizing a lot of these capabilities so that we can bring more of these capabilities to be deployed in additional custom environments, like non-NASA environments, or pay-as-you-go, where someone on the academic side, right, a university could have their own Amazon environment. Could they deploy some of these MAP capabilities in that environment? But at the same time, we're recognizing through those green areas that there are certain federated services that make sense to have centrally managed, right? It's not just CMR, right? But it's other registries that are unique to this science domain. They actually have hyperspectral spectroscopy algorithms in public repositories. And could we have those as part of the federated services where you could fold in and bring in and load in these algorithms that are domain specific and load them into this environment, this map-like environment, and then deploy and run at scale effectively. This is the last slide, so hopefully Doug is okay with this. But one of the key elements of this was open source science, right? Everything we talked about was about how do we work in a collaborative environment? How do we democratize those capabilities so that users have access to a lot of these capabilities themselves, right? It's not just the code, it's the capabilities that they can do themselves with all of this code. So I think what we realize is that there actually needs to be a lot more emphasis on not just the open sourcing the code, but it's the whole thing, the end-to-end, right? It's the governance, it's the documentation, and effectively it's like what we've been calling a community of practice. Actually, we've been having lots of different meetings across different organizations about a community of practice. And I think that the overall theme here is that there are a lot of different organizations now contributing to this. How do we have, in a more open source science manner, how do we coordinate in this, right? What happens if one project needs to make a change? How do we communicate that information across the other? How do we reap the benefits of this open source science model? And it's even more pressing now because now Natasha's from her university side, she's bringing in NSF capabilities that we want to integrate together. So now we're trying to bridge that gap as well. And I'll end with that. Yeah.
Any questions for Hook? Again.
Thank you. I'm curious. I just feel like I'm not sure exactly how to say this. It does seem like some of those diagrams are pretty complicated, and I think, at least for me personally, the project sounds more and more interesting the more you talk about making it relevant to people outside of the NASA mission. So that seems like a very difficult problem from my point of view, just because the more buy-in you have, the more responsiveness and issues you're going to deal with outside of NASA, it's going to create more work for the people who want to develop that code. So there's going to be a balancing act, and I think at some point you're going to have to decide, we want the community, or we're going to make these the priorities for now. Or I don't know if you've thought about that at all, but I think it's very difficult.
Yeah, I think Hook can go into the details on this, and as you know, with great acumen. But at the administrative level, I'm actually going to walk into another meeting in a couple minutes, and that's exactly what I'm going to talk about. We've got map clones popping up. We have to support them. I'm going to say, yeah, he was just watching me do the PowerPoint. So we are going to put resources into dramatically upgrading the documentation. I mean, it's certainly documented, it's released, but we're going to make it a lot better. We're going to talk about how many resources we want to put into, like what level of help support do we want to put into this. We're talking about modularity of map, because obviously if you're not in NASA, you probably don't want to use CMR for your catalog. And there are clear, like you don't have to use CMR, but it's a little clunky if you don't have a catalog. So we're going to try to look at making that clear, for example. But yeah, we are on that, and I'm talking about in 5 minutes to the higher level people.
I can also.
Any other questions other than clunky?
I can add some.
If you don't use CMR.
Let me add one more insight here. I 100% agree. And actually, it's great to hear Stinger say that. I mean, from a headquarters perspective, it means that there is support. There is agreement, and they're trying to work with us, right? And let me try to answer your question in a different way, but I'm going to tie it back to open source science, which is that the questions that you're raising, I think, were part of the interesting set of questions that have already been raised in all of our community of practice meetings. An example is, should some of these services, actually in the prior diagram there, should it be owned by the community? Should it be hosted by NASA as a whole, NSF as a whole, or should that be the onus of a specific project? What if it's on the project, then how does that get reused? These are all the questions that were raised, and we don't have answers to those, but we need headquarters' help, and maybe NSF's help. So, but this is why I think open source science is useful, because it's part of a community process. So like, we need your help, right? You're part of the community. We don't want to own this any more than you do. So, I mean, you know, it's open source science, right? I hope I didn't say anything controversial.
Are you done? All right, I'd like to thank Hook twice, Sujin, Kaylin, Amy, my ESIB fellows. Go eat your lunch.